Hi everybody. Is it Tuesday? Is it Tuesday or Wednesday? I think today is Tuesday, right? Yeah, yesterday was Monday, so okay. Hey, we're happy Tuesday, and we're gonna do some stretching. Okay, so like full arm rotation. Oh, and neck rotation. This is what I do during my break time. Ah, but today I was busy, so I didn't have time to do this during the day. So I do it now. Then waist rotation. Waist bending to the side. Then waist bending to front and back. Oh. And then squat. Then knee rotation. Knee rotation. You wanna see knee rotation? Like knee rotation. Then maybe ankle rotation, crunching your toes, ankle rotation, make fist with your toes, same with your wrist. That's that. Alright, let's begin the chair, make the right angle, and get it started. Let's get the party started. Our mathematics party. Well, we tried to prove Fermat's last theorem in an easier way, but we failed yet again. But hey, third time is a charm, right? So yeah, we keep on trying. Hopefully this time it works. Yeah, I do have some different approach to take. We are going to step way back. We really go back to the basics, okay? We will. Okay, give me 1 second. Gotta switch out this board. Uh, you remember the triangular enumeration method that we've been taking in Euclidean algebra? Yeah, that's what we're gonna do. We'll enumerate numbers, just like Pascal's triangle. Okay, we're gonna build another triangle. We call it Pythagorean triangle. Okay, because we already have Euclidean triangle, right? We call it Pythagorean triangle. Okay, so or we can call it Pascal's triangle of the third order. Actually, maybe it's better that way. Better name it that way, because what we're gonna do is what Pascal did was binomial coefficient, right? We're gonna generalize that. We're gonna make multiple, more than two, three and on. Okay, so that's, and we'll try to find a way to build that kind of triangles. Probably like 3-dimensional, 4-dimensional pyramids, right? no problem. We've dealt with that before. We have done pyramid numbers before, right? So we know how to do it. All right. So n dimensional, no problem. We know how to do it. Uh, well, it's raining. It's raining in Alaska. It's just good. It cools down the weather. So, uh, Pascal's triangle is just there are just two variables inside of the parenthesis. Then you have, well, as a starter, okay, you have a plus b to the 0th, to the first, to the second, and they are the coefficient, right? Now, what we're going to do is we're going to add one more term, okay? So we're going to have a plus b plus c to the zeros, to the first, to the second, and on, okay? So, probably it's combinatorial problem, right? So probably we can do something similar to this Pascal's triangle, okay? I haven't seen anybody doing this. Probably it already exists. That would be my guess, but doesn't matter. I'm not going to look it up, okay? Or I might. Why don't I look it up, okay? No, I'd rather do it on my own, okay? So we have this 1 and 1, 1, 1, right? And here we have 1, 1. And then what? A plus b plus c squared, that is equal to a squared plus b squared plus okay. Here you have a squared plus 2ab plus b squared, right? Okay, so how many twos do we have? 1, 2, 3. We have 3 twos. Okay, I think I know how to do this. Alright, it goes like this. You have 1 and 1 and you have 1 above, okay? So that's why there are 3 twos, okay? So you know what? We are not going to complicate too much, okay? So 1, 1, 1, but you have to see this in a 3-dimensional way, okay? Because this will be 3-dimensional object, okay? You have to do it 3 times, like the first and third guy, the guy in the middle, think of it as it's hovering above this whiteboard, okay? It's 3-dimensional, okay? So if you do that, you have 2, 2, 2, okay? And then above this, we have 1, hovering 1. We'll put hovering 1 as something like this. What I mean is this. in Pascal's triangle is two-dimensional because there are only two terms here. But in let's say this is second order Pascal's triangle. Let's say this third order Pascal's triangle. Okay, what you have here is you have 1, 1, and 1, but this third one is above this plane. That's why it's three-dimensional. Okay, now in Pascal's triangle, because it's two-dimensional object, you only have two sides, left side and right side, right? Bottom is triangle, so it's a triangle. It's a two-dimensional object. But here we are dealing with some kind of what tetrahedron. What I don't know what. What is this object? I don't know what the name of this object is. I used to know tetrahedron. You know, it's best if I bring in my cell phone. Okay, so some kind of pyramid. Okay, that's what we're dealing with here. Tetrahedron. Is what this called? Yeah, it is. Do you have something Pascal's tetrahedron? Let me see. Pascal's pyramid. Okay. Yeah, they have it, but I didn't know. I didn't know. It's in Wikipedia. It's called Pascal's pyramid and trinomial distribution, trinomial expansion. Okay, okay, okay. So they have it. Good. Do we have four-dimensional thing? Multinomial coefficient. Okay. Mm-hmm. They have something like that. Yeah. Good. I'm glad that it's already there. Mm-hmm. They put it so nicely here. Yeah, this Wikipedia is that all mathematicians who contribute to this Wikipedia article. So, yeah. Oh, yeah, it's beautifully done. This Pascal's pyramid is done very beautifully. Very good. Okay, so oh, that's great because we can just take advantage of what they have done here. So that's good. So the Fermat's last theorem, mathematician in what 1700, Leonard Euler, German mathematician. He tried to generalize it, but there was a conjecture and it was proven to be wrong. Probably in 1900s. It wasn't very long ago. It was like 50 years ago. Probably in 1966, something like that. From what I remember. Okay, so it's fairly recent development, relatively speaking. So obviously it was a challenging problem even to Euler, the great Euler. Okay. Proving Fermat's last theorem. So they found some examples in counter examples to this Euler's conjecture in fourth and fifth order. Okay, that's fine. We can find some necessary and sufficient condition for Euler's conjecture. Where we can find out when it's true, when it's false. and possibly it's as difficult as Galois group theory, or his polynomial theory, his proof of that the Udo fifth and above equation doesn't have any algebraic solution kind of stuff. It may be as difficult as that, but well, so what? So what? We'll take a shot at it. Okay. All right. So let me take a look at this Pascal's pyramid for a little bit. How they constructed this thing. It's beautifully done. Yeah, look up Pascal's pyramid. It's very beautiful. Very interesting. Okay. I appreciate all this hard work these mathematicians ever did. Yeah, very diligent. Ooh, these people are really hardcore. All right. Yeah, some people say there's some application in genetics of this Pascal's pyramid. Well, that's interesting. Whatever. Okay. Um, let's see layer three, third stairs in this Pascal's pyramid. Because we did some calculation back there, right? Yesterday. Three sixes, one, two, three, one, two, three. Okay. So we got the calculation correctly. Good, good, good. Okay. And we probably not do third order, okay? Because it becomes too tedious, okay? So $1 million, Bill's conjecture, which is related to Fermat's theorem, or Fermat's last theorem, alternative proof. We may have to let it go, okay? Why? I exhausted alternatives. I don't know how to do it. Okay, I gave it 3 trials and it's not working. Okay, so none of them worked. Okay, so um, it just gets too bulky, too tedious to expand this polynomials. It becomes too mechanical. Okay, I mean even to me, I don't want to do it. Okay, I don't want this. We may go back to this Euclidean square, and try to come up with definite formula for Euclidean number. Okay, algebraic fixed form formula for it. We may or we may not. Doesn't matter. We'll keep on trying, and then move on. Okay, so as you remember, our holy grail is to find fixed formula form for prime number. Okay, that's a very ambitious project. That's our holy grail, our big goal, bigger, larger goal. Euclidean square is something we ran into on our way home. Okay, prime number formula. So this we did it as a distraction, fantasizing about $1 million, like how to spend it as a distraction because we need to take a break from all that new ugly duckling Euclidean square. Okay, it just give us nice break, something exotic, you know, like mathematical gentleman's club kind of. Okay, this is like $1 million prize. Very much less theorem, whatever. But we're not gonna go there. Okay, I don't see any light at the end of this tunnel. I don't. Do you? Then go for it. I don't. All right. But it's nice to see that Pascal's pyramid is very beautiful. The way they constructed it, kind of, laid it out. Yeah, it was very beautifully done. Okay, so yeah, I appreciate other mathematicians, what they have done, their hard work. Yeah, it's beautiful. And contributors to Wikipedia. Yeah, appreciate that. Okay, let's let this go. Okay, yeah, it's a fascinating field, but I just don't see any light at the end of the tunnel. Let's give it 5 more minutes because I don't feel like giving it up like that. Oh, I forgot to tell you, parameterization. I kind of remember what parameterization is. You have Euclidean, I mean, Pythagoras triple, right? Pythagorean triple. And Euclid said, let A be what? X squared minus y squared. B is what? 2xy. C is x squared plus y squared. This is actually parameterization. Why? What is parameterization? You have in this equation, you have three independent variables, right? Three variables, and they're like input variables. Okay. This whole thing can be thought as Boolean function, some Boolean function whose input is a, b, and c. Depending on a, b, and c, this function can be true or false. Okay. I mean, typical way in mathematics, you say a squared plus b squared minus c squared is 0, and this is some function of a comma b comma c, right? But we rather do it this way. Okay, we just call this whole equation as a Boolean function. This could be 0 or false. Okay, because we love Boolean algebra. Okay, so all right. So input of this function becomes output of some other functions with some other variables. That's what's called parameterization. Okay, input, we express each input of this function as some output of some other function, other functions with some other variables. Okay, so for Fermat cubic, okay, just I'm sorry, cubic, Fermat cubic. Fermat cubic, 3, 4, 5, 6. Okay, I learned. They parameterize this with two variables. From what I read in Wikipedia, okay, S and T. Wikipedia is nothing but they all came from mathematical journal articles. Okay, so contributed by some mathematics students or mathematics professor, most likely mathematics students. Okay, in their spare time, I guess. Okay. Yeah, Wikipedia is just placeholder. Okay. So it's just easily accessible way. So yeah, I like Wikipedia. I read it all the time. Okay, they're cool. Okay. It's just that they can be nicer. That's what I'm saying. Okay. And less liberal. They tend to be too liberal. Now, the way they parameterize this, they use S and T, only two parameters. Okay, I don't think it has to be that way. You can use three parameters. Probably it will come up with, because their parameterization is quite complex. Okay, but if we use three parameters instead of two, probably we find an easier way to express A and B and C in terms of X, Y, and Z. We'll take a shot at it, okay? And if we don't get anywhere, then we'll just really move on, okay? We just give it one more chance, okay? We had that kind of experience before. We wanted to move on, but let's give it one more try, and then all of a sudden, we found some kind of breakthrough, okay? So that may happen here, okay? So we'll take a break, and we give it one last shot. All right. So I hope it works. I hope so. Okay. It may not be too difficult. Who knows? Who knows? All right. Um, I'm feeling that we're gonna have some fun with this. All right, because we're gonna design some Diophantine equation because now we have a lot of data to play with, to test out. We're gonna have some fun, okay? So it's good that we keep failing because then we feel so free to erase. Because if you discover something, we don't want to erase, you know. If it's a failure, oh, no problem, erase it all because it's a failure. Some silver lining on this cloud, I guess, makes our life easier. We don't have to try to choose. Oh, I don't want to erase that whiteboard. Oh, so okay. I want some different color though. I wonder how these pens are doing. It's too light. Light. Not too bad. Well. Okay, let's try this. All right, so you have a no, this isn't gonna work. How about this black? A little bit better. Yeah. A to the third plus B to the third plus C to the third is equal to D to the third. Okay, this Fermat's cubic, something like that. Fermat cubic, something like that. Okay. We want to design some Diophantine equation, some parameterization that kind of resembles this Euclid's formula, right? A is what? X squared plus minus y squared. B is 2xy. C is what? X squared plus y squared. We want to design A is A of x, y. A has three variables, okay? X, Y, Z. Okay, X, Y, Z. This tensor, extended tensor notation, all right? Because we don't want to do parentheses. We need to save space, you know. Low budget. Okay, so all right. Also D also is x, y, z. It's a function of the three variables, each of them. Okay, so and we have formula for a plus b plus 3 cube. We have formula for that down there. Okay. Maybe it's not that fun because just by staring at that, it's a mess. Oh boy. But we'll give it our last shot. Okay, so because we don't want to really just give up, you know, just because it's difficult. Okay. Okay. Well, let's start easy. Diophantine equation, okay? We want to design this such that this is 3, 4, 5, and 6, okay? I mean, for example, Pascal's, I mean, the Euclid's example, you know, Euclid's example, okay, this guy was what, 3, 4, 5, right? So yeah, x is 2, y is 1, then it works perfectly, right? We gotta try something like that here with some. It has to involve second order because you have second order term here. X and y, x times y, they are combined together. They're second order because it's x to the first times y to the first. 1 plus 1 is 2. Okay, so that's how you determine the order of a term. Okay. You regard x and y as the same thing, okay? Let's think about this for a second. Because we have Diophantine equation, that's why it's going to be interesting. We are designing function of 3 variables of third order so that each of this becomes 3, 4, 5, 6. That's why it's going to be interesting, okay? It's a puzzle, mathematical puzzle. Recreational mathematics, okay? Yeah, it's going to be interesting. Okay, well, let's draw some nice table. 1 to the third is 1, right? 2 to the third, uh, not 7, 8. 3 to the third, 27. 4 to the third, 64. 5 to the third, 124, 125. 6 to the third, 7 to the third, right? Uh-huh. With 50 times 7, 350, right? Minus 7, yeah. 343, okay. I know how to calculate this without like scribbling down because I did enough mathematics in the past. Okay, so oh boy. By some combination of this, we should come up with 3, 4, 5, 6. Okay, by some manipulation like multiplication, or maybe times multiply each other or multiply by some constant or even square, I don't know, but we should come up with number 3, 4, 5, and 6. Okay, so that's our goal. It's an easy task. What about x, y, z? Yeah, x bigger than y, bigger than z, bigger than 0. Or it could be equal or equal. Yeah, I guess it could be equal. Okay, let's relax the constraint a little bit to make it a little bit easier. Okay. So, okay. But another constraint, each term has to be third order. All right. Let's make some easy hypothesis. How about that? Some easy hypothesis. Let's go back to this Euclid's formula, okay? A itself doesn't have to be some perfect square of a number, okay? A doesn't have to be perfect square. A in this example is 3. It's not 3 is not perfect square. Because square root of 3 is irrational number, like 1.732 blah blah, right? So likewise, A doesn't have to be perfect cube, okay? Just one hypothesis. What if A is equal to x cubed plus y cubed plus z cubed, where x, y, z and where x, y, z is equal to 1, okay? That's one hypothesis, okay? And then you have 3 squared plus 4 squared is equal to 5 squared, right? X is equal to 2, y is equal to 1. I'm I guess I'm a little bit confused. Yeah, A3. Hmm? Now B is supposed to be 4. Okay. How about B is equal to, I'm just randomly guessing here, really. Hmm. Mm. Mm. Okay, I guess this can be D. Sure. Dude, there are 6 terms there. Yeah, we rearrange it later. Okay, so. Okay, well, let's arrange it now. We may be onto something. I don't know yet. Four and five. That can be very tricky. Yeah. Okay, 6 is equal to 8 minus 1 minus 1, right? So what if x and y are 2 and z is 1? I mean, x is 2 and y and z are 1. Hmm. Boy, this is not easy. This is not easy at all. Well, we know this is not gonna work because if you cube this, cube that, probably no. Um, God, goodness. I don't think I can do this. Okay, yeah, it's way above me, really. It looks simple, but it's not. Hmm. One thing I noticed though is this. if we subtract 8, if we subtract 1 from 8, 8 minus 1 is 7. If subtract 8 from 27, that was 19, right? 7, 19. Subtract 37, subtract your 1, and then what? 61. Subtract 9. No. You're subtracting in opposite ways. That's why it's so confusing. Okay, so. Okay. You subtract 7, 2, 1. They happen to be all prime numbers, okay? So probably it's already known, okay? You subtract cube of two consecutive numbers, it becomes prime number. Well, I didn't know. I just noticed. I'll look it up, okay? You have two consecutive the cubes, right? You subtract them, it becomes prime number. I just noticed. But they are not like consecutive prime numbers though. Okay, so how about square? Yeah, this one isn't working. Okay, so we're gonna we give it up. But we discovered something interesting. Probably it's already discovered a long time ago, but whatever. Oh yeah, here you have 3, 5, 7, and then what? 9, 11, right? Well, let's keep moving. There's just a bunch of odd numbers, right? Okay, well, whatever. Okay, here we have set of odd integers. Okay. So subtraction of two consecutive cubes, prime numbers, not exhaustively, but some subset of prime numbers. Is this prime number? Well, I gotta bring my cell phone. It's charging now, so let me look this up. It's kind of interesting. Probably because something very easy. So I'm pretty sure it's already discovered. But hey, we found something. Okay, we're learning something. Even if it's already discovered, but doesn't matter. We can generalize this too. Okay, so maybe two consecutive power of some odd integer, maybe. No, not really. Maybe some power of some prime number. Subtract that, and then it becomes prime number. I don't know. Well, we'll see. All right. Take 5, okay? All right. This could be new. I couldn't find it. Maybe it's already there. I don't know. Could be new. Well, let's see. Let's expand this thing out. Who knows? Um, Give me 1 second. I'm kind of excited. I mean, we're not gonna win $1 million, but we may have found something. It could be new. Who knows? Let's expand this thing out. Okay. So what? It's very easy, right? N plus 1 cube minus n cube is what? 3 n squared plus 3n plus 1. Is this always prime number? Let's look this up, okay? The way I look it up, I just do like 3 times n power 2, blah blah blah, right? So I'll be very surprised if this is not already found. Is 127 prime number? Let me look that. Oh, yeah, it is. Okay, well, I'll be very, very surprised if this is not already known. Or it could be false. Let me look it up. Better be known. I mean, this is elementary. If it is indeed prime number, always. Oops, I made a mistake. I mean, there's something similar, but not exactly. Okay, Bing search is not giving me any result. So let me go to Google. Sometimes it's better, web search engine. So Well, there's Wikipedia article about Collat's conjecture. Let's see what it is. No, it's not that. It's not this. No. Is this always prime number? That's my question to you. I don't know. I mean, we can factor it, right? Partially. Can we disprove this conjecture by making some counterexample? We are trying to make this non-prime. We know this is always a multiple of 6. Okay, because n times n plus 1, it contains 2, even number. And if you have 3, so this is like what? Here you have what? N is one or more, right? Okay. And this is 6 times k plus 1. And if n is 1 or more, then k is what? One or more, right? When n is 1, k is 1. When n is 2, what is k? K is odd. Two, 1 m 2. Okay, so when this is odd number. Okay, so okay. What if n is 3? 3 times 2 times 2, 3? Okay, let's see what k can be. Alright, when n is 1, you have 6 times 1, so when n is 2, when n is 3, when n is 4, really? What kind of sequence is this? So basically k is n n plus 1 divided by 2. That's what k is. When n is 1, 1, 2, 3, 4. Okay, 4 times 3. Ah, 3 times 4. 3 times 4. Okay. 4 times 5. 4 times 5. Okay, okay, okay. So that's what k is. Okay. Can we make this a number that is not equal to prime number, non-prime number? Can we make this into a composite number? Okay, so that's my question to you. We know it's always odd number. And this k isn't just any integer, okay? It has to take this kind of form. Okay, I'm trying to find some counterexample to this conjecture, all right? Is this always prime? Because I don't find it in the internet. Can we prove or disprove this is always prime number? What a nice exercise. You know, sometimes we take a break from mathematics, right? But inside of mathematics, we want to take break from that Euclidean square because that's just too long. Okay, so we do some other mathematics. Okay, we're taking a break from a break from a break, break in a break in a break, kind of. All right. So, for example, when k, let's just give you the example. Okay, when 6 times 4 plus 1 is 25, right? But 6 times something plus 1 tend to be prime numbers. So it's kind of this kind of form is very dense in terms of prime number distribution. Okay, like number 7, number 13, number 19, right? Next 25, yeah, that's composite number, right? But looks like this form is very dense. It's a dense, this kind of family, this kind of subset of integer, natural number, is very rich in prime numbers. Okay, so just some observation. We are looking at density of prime numbers in a subset of natural numbers. Okay, yeah, it's kind of useful concept. I'm pretty sure it already exists, but if not, well, we are giving some new way to look at prime numbers. Okay. For 4, four is not k, because k has to be specific form like this. All right, so 4 is not one of those this k sequence. Okay. Well, let's make some more example. When k is 5, 31, right? Again, it's prime number. When k is 6, 37, again, prime number. So this is a very high density family of subset of natural number. Okay? So no wonder when we restrict k, it's at least even denser in prime numbers than this guy. Because we have yet to find some counterexample for this. Okay, this is conjecture that this guy is always prime number. Okay, I'll be very surprised if it is, because it's something extremely elementary, something I just noticed. If it is indeed always prime number, then and it's already not yet known, that will surprise me, because it's something very elementary. Okay. Well, we'll see. Let me grab my blanket. It's a little bit chilly. I'm gonna cover my legs. Let me turn on the heater, man. Oh. Yeah, I turned the heater on. Prime numbers. What a fascinating subject. See? 6 times 7, 42. Plus 1, 43. Prime number. 6 times 8 plus 1, which is 49, which is 7 times 7. That's interesting because we may have found something, okay? Because the first known prime number is happen to be square, perfect square of 5, which is a prime number itself, 5. And now you have 6 times 8 plus 1 is equal to 49, which is the next prime number square, okay? Let's keep on going, shall we? Because this is interesting. Okay? I mean it. This is fascinating. Well, it breaks it breaks the pattern. Okay. Oh well. But at least it's prime number times prime number, right? Okay, let's take a look at more case, okay? So, um, oh no. How about 6 times 15 plus 1? 91? Prime number. We keep on going, okay? So, 6 times 21 plus 1. Prime number? How interesting. Let me see the list of prime numbers, okay? Because that's there. I just want to verify. They are indeed prime numbers, okay? How interesting. Oh, 91 is not prime number. Good, good, good. Okay. I'm glad. I didn't want this to be prime number always because then it'll be too easy. Yeah, it does look like prime number, doesn't it? But I guess it's not. Okay. Is it like 13 times 7? Good, good. Okay, okay. 13 times 7. So we just disproved it. Okay, very good. Whew. Well, that was interesting exercise, right? Yeah, that was interesting. Yeah, 91 is not prime number, okay. Yeah, it's 13 times 7. You know, prime number times prime, it almost looked like prime many times, okay? Because it's just not easy to find some division, you know. So, all right, good. And do you really want to go back to that Euclidean square? Oh, I don't think I have taken enough break from that because if you have taken long break from Euclidean square, then you probably will want to go back to it because it will be fresh to us. But right now, for now, no, it still feels very stale to me. So I need some more break from Euclidean square. Okay, so um, let's explore this because are there so there's this whole set of prime numbers, right? But are there some kind of that looks like this, some kind of simple algebraic formula that consists subset of all primes? Okay, provably so. So that's my question. Are there ones that other mathematicians have discovered that express a certain subset of all prime numbers, prime number set? Okay. Has there anybody who found that, provable and proved that it always is prime number? I don't know. Let me look it up. 'There's some journal article here. 2012 is relatively new. Okay. From Lebanon. Interesting. Yeah, it's interesting, but it's not quite what I'm looking for. I want some algebraic formula like that. 6m plus 1, yeah. They, yeah. Somebody already found, yeah, this 6k plus 1 tend to be, or there are a lot of prime numbers in this family, 6k plus 1, but not always. So somebody already noticed that. That's good. Yeah, I'm not sure if anybody found such definite formula. We got pretty close. The first non-prime number, that's what's called Masny prime. It's like two prime number that's in the form of 2 to the n minus 1. But is it? Mm-hmm. But when n is equal to 4, 16 minus 1, that's 15, right? So that Masny form, I don't think it's very dense in prime numbers. Okay, but this form probably is a lot denser than Masny form. Okay, so let's formulate this problem. Okay, we'll call it prime subset problem. Prime subset problem. Okay, this entire set of prime numbers. Okay, we want to find some easy fixed form algebraic formula. It's not an equation but formula that is truly a subset of prime numbers, no, without any exception. Okay, that's the prime subset problem. All right, so let's try to solve that. Let's try to find a formula, some basic algebraic formula that results in always a prime number, but not all the prime numbers, but some subset of prime numbers. Because we came pretty close. Okay. I want to refine this expression so that no matter what we find, is always prime number. Okay. So 91 is the very first non-prime number, and when what? N is equal to 5. When n is equal to 5. Right? We need to get rid of this guy. Where our natural extension would be how about n to the cube minus 1? Oh, this won't work, right? Because this alternates, right? Even number, odd number, even number, odd number. So this won't work. Okay. Because we want this algebraic expression to be always odd number. Okay, because even number is not a prime except for 2. Okay, so how about n plus 2 cube minus n plus 1 cube minus n cube? Is this even number or odd number? Or does it alternate? I don't know. Let's just make one example and we'll take a break, okay? So 27 minus 8 minus 1. No, it becomes even number. Okay, so okay. The question is this: is it possible there to find a formula? Does there exist a fixed form, fixed algebraic formula that always result in prime number? Is that even possible? That's the question. Okay. But it doesn't have to every single prime number. It could be just subset of prime number. Of course, our holy grail is to find a fixed formula for all prime numbers. Okay, that's what we are after. Okay, but an easier problem would be: can we express only a subset of prime numbers with a fixed formula, closed form formula? That's the question. Okay. I mean, Masonic form, that's nice. Like 2 to the n minus 1. Prime numbers can have that kind of form. But 2 to the n minus 1, when what? N is equal to 4. Yeah, 16 minus 1, 15. That's not prime number. Okay, so I mean, even as simple as what? 2k plus 1, right? Odd number. Are there prime numbers that's odd? Yes. Every prime number except 2, right? Yeah, so you can say 2k plus 1 is one form that many prime numbers conform to. But there are so many other numbers that take form of 2 and 2k plus 1 that is not prime number, right? Okay, see what I'm saying? Yeah. Let's see. Let's see the very first occurrence of this prime number, okay? Uh, 1, 2, 3, 4, 5, 6, 7, 1, 1. That doesn't quite work. Never mind. Okay. All right. Oh well. You know. Uh, Wait a minute. This is just a set of odd integers. Oh, forget it. Yeah, because a squared, a plus 1 squared minus that is 2a plus 1, then 2a, right? I mean, no. Okay, 2a plus 1 times, yeah, it is 2a plus 1, okay, so. I'm wondering the distribution of prime numbers. Does it get thinner or thicker? Let me look it up. Distribution of prime numbers. Isn't that the prime number theorem or something? Uh, 1 over log n, so becomes 0. Yeah, another mathematics journal article visualizing prime distribution. Okay. You know, after this recording, I probably try to find out and watch the documentary about Professor Andrew Wiles, how he found this his proof about it. It'd be interesting to watch. Probably be safe to watch too, because I don't want to pollute our own independence with by watching too many, by learning too much. Okay, so if you want to maintain certain degree of creativity and also independence. Okay, so yeah, that's why it's kind of important. Okay, so okay, we'll take a break, Benson. All right, Luxembourg. How interesting. Well, it seems prime numbers distribution of thereof it gets thinner and thinner. I think that's the prime number theorem. That's what it seems. It gets like rarer and rarer prime number as number grow very big. That's what it seems, which makes sense because intuitively speaking, you have multiples of twos and multiple of threes, multiple of fours, multiple of fives. And the very first prime number, like 7, it has its own multiples, right? Next prime number 11, right? It will have its own multiples, okay? And next prime number, number 13, it will have its own multiples, like 13, 26, 39, and on, right? So that's why the next first prime number it will be farther away, farther and farther away. But the next prime number will be a lot bigger number because all the previous numbers they are already multiples of some other previous primes. Okay, so that makes intuitive sense, right? Yeah, it does. Okay. You know, because this Euclidean square is really blocking us. Okay, so we may just leave all this Euclidean square triangle. We may just want to leave it behind us and just move on to reach our holy grail prime number function. Okay, we may just try to do that. Okay, so because this LCD, GCD, that's just very small part of what we are trying to do. Okay, so we want to find a formula for LCD, and we realize it has to do with GCD, and then we got stuck in GCD. Okay, we spend way too much time in GCD, but efficient algorithm already exists, so okay. So it'd be nice if you can find fixed formula for Euclidean number, but we don't have to. It's not that necessary. All right, so we just move on, okay? Because that's blocking us. Just like Jesus said, if this branch of you makes you sin, cut it off, okay? In humanology, we only interpret it in metaphysical fashion because we don't advocate for amputation, right? metaphysically speaking, that branch of what we are doing, the Euclidean stuff, is blocking us from progress toward our goal, prime number function. So we just cut it off. Okay, we forget about all the. We even erase that shit. Okay, so because it's kind of ugly. We're gonna erase. We're gonna forget all that, and then we'll go on with the prime number function because that's retarding us. That's slowing us down. All right, so we'll just get rid of it. All right, so let's take a break, okay? Because this room is overheating. All right, so take 5 to 10 minutes break, okay? So. Whew. Okay. Alright, we are back. The rest of today will be very easy. Okay, we have what, 1 hour left or 40 minutes left. It'll be nice and easy. Okay, because we dealt with some very difficult mathematics for past few weeks. We are not going to deal with any of this anymore. Okay, we'll just get back to our main course of action, investigation. Okay, most of it is we already figured it out, most of it. Okay, so it really nothing. Let's review. Okay, so how about prime counting function? Okay, so we believe we can find prime counting function closed form algebraic expression, but before we do that, we'll have to approach from the set theoretical point of view. Okay, so it's this. Okay, let's say M is set of multiples. You have A and B. Okay, so A is the upper limit. Okay, find all. This is traditional set notation. Okay, small m is multiple. I'm not going to English. M is some multiple of B, KB, where now we have a list of conditions. K n plus positive integer, okay, natural number, I plus, okay, and okay, that's that. For example, 10m2 okay, multiples of 2, there's 10 or less. Okay, so that's it. All right, and then we're going to define a proper multiple set mu. We just use mu. Okay, lowercase mu, because I don't know how to write uppercase mu. Maybe it's just m. We want to distinguish that, so we just do it. Okay, so it's just 4, 6, 8, 10. Everything except the 2. Okay, so a mu b is equal to a m b minus b. Okay, it's the same as just b. All right, it's that subtraction. Okay, so we have that, and we know what's absolute value. Well, how many members are here? Ten divided by 2, right? So what if this is 11? Okay, so okay, a divided by 2, right? And we don't like this ceiling, this floor function notation very much, but just for now, okay, we're gonna take it nice and easy today. And then minus 1. All right, so that's that. I mean, e. Okay. All right, something like that. All right, so instead of this, we prefer using this quotient notation, right? A quotient B minus 1. Okay, that's compact symbol. When A is divided by B was the quotient. Okay, that's it's just like row algebra kind of, right? So, okay, so yeah, that's that. We know this before. We knew this. We formulated this before. We saw review. All right. So now, so this upper limit number 10. Okay. So we are trying to find this prime counting function. Okay. Prime counting function. That's what we are trying to do. Okay. So, for example, we don't have to care about one. Okay, it's just 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, how many prime numbers are there? Each of which is 10 or less. 1, 2, 3, 4. So prime counting function pi of 10 is 4. Okay, we want to find formula for that. That's easy because uh, we only need to examine when it comes to multiples. We only examine 1/2 of that. Okay, because are there any multiples of 6 in this set? No, because 6 times 2 is already more than 10. So there's no multiples of 6 other than itself. Same as 7, 8, 9, or 10. Okay, so okay. Okay, so what I'm saying is proper multiple set of 6 is empty set. Okay, so we don't need to care about that. Okay, because the way we're going to approach this is out of this set from 2 to 10. Okay, that's the universal discourse. Okay, we subtract set subtraction multiples of 2, multiples of 3, multiples of 4, multiples of 5. And then what's left is the prime set. Okay, so let's say the set of primes, each of which is less than 10. Okay, so set of prime, you have what? A set of primes B. Again, this is a review. All right, this is you have set B no set A contains by definition all the natural numbers from 2 to A. Okay, so set A is equal to x okay. set subtraction, then union k from 1 to um, a quotient b, no, a quotient 2. Okay, we only need to examine just one half, alright? So mu I'm sorry. No, sure. 2, 3, 4, 5. That's all we need to examine. Okay, so yeah, something like that. Okay, and so we have union, right? To absolute value of APB. Okay, this is the pi a. All right, so we have prime number set and number of prime numbers. That's the prime counting function. Okay, so this is absolute value of that. Okay, so absolute value of this guy is pi of a. Okay, so and to do that, we need to know what this guy is, right? Because we know what this guy is. It's just what a minus 1, right? And once we find this guy, all we need to do is just subtract. Okay, so it all boils down to counting the number of set unions. Okay, it's just like a union b union c is equal to a number of that is a, number b, number c minus number a b, number b c, number c a plus number a b c, right? So that's what is number a b? That's the set of the least common multiple, LCM. Okay, so that's why we did LCM and GCD. I'm just too tired now, and tomorrow I have to wake up very early. So we just wrap it up here today, and we'll pick this up tomorrow. Okay. So now we are back on track. Okay, so this is all review. Okay, but there's some more efficient notation here. So I'm not going to erase this, but I don't want to write this down now. I'll write this down probably tomorrow because I'm too tired. Okay, so yeah, I promise you, it'll be easy from now. Okay, so yeah, a lot easier. We deserve some nice and nice and easy work because we've been dealing with very difficult problems lately. Yeah. Do I really want to look at the documentary about Andrew Wiles? Maybe, maybe. but I yeah, I kind of don't want to think about mathematics because we've been doing for 2 hours. But we'll see. Okay, thank you. Good night. Bye.